Over general regions. In the last section, we considered using double integrals for several selected applications over rectangular regions. In this case, we can use the double integral to find the area over pretty much any region as long as it's bounded by known functions. In the first case, we have a top curve, y equals f of x, and a bottom curve, y equals g of x. And we go from x equals a to x equals b, and we want to find this area. And we can simply integrate dy dx. The best way to think of this is x first. The x on the outside goes from a to b, so we go from a to b. You can say x equals if you want to make that explicit. And then for each x, y goes from the bottom to the top. It's always bottom to top. And of course, sometimes we have x as a function of y. In both cases, just depends on the circumstances. And in this case, you can do a dx dy integral. Set up y first. Y goes from a to b. Outside, always constant. That's a good point to make. Y equals. You never have, if it's over a definite region, you will never have a variable on the outside. That's the last integration you perform. You should be able to plug in a number and get a definite answer. And then inside, we go from left, g of y, to right, f of y. Notice these limits always go in increasing order, bottom to top, left to right. If you were to switch one of these, conceptually what happens is x would go from here to here, dx would be negative, it would give you a negative integral. If we went from b to a, f to g, we would have negatives times negative is positive. We get the correct answer because of the cancellation of the negative signs. But both integrations would be backwards nonetheless. Here's an example. Let's use a double integral to find the area bounded by y equals x squared and y equals 16. Fairly simple example. Easy to graph. Y equals x squared is a basic parabola. Y equals 16 is this. You can set x squared equal to 16. X is plus or minus 4, so we have that's 4, that's negative 4. This is the area we want. So we're going to set up area as a double integral, dy dx. Again, x goes from negative 4 to 4. And then we want y to go from lower to upper. Lower is the parabola x squared, and the upper is y equals 16. So we can go ahead and evaluate that. Negative 4 to 4. Y from x squared to 16 dx. Plug in 16, plug in x squared, we get integral of negative 4 to 4. 16 minus x squared dx. And 16 gives us 16x minus x cubed over 3. Now, if you don't feel like doing the positive and negative thing, this thing is symmetric. You can always do times 2 times 2 and then go from 0 to 4. That will simplify it. And that'll give you 2 times 16 times 4 minus 4 cubed over 3. And that's 2 times 64 minus 64 thirds. Okay, which gives you 2 thirds times 64, 2 times 2 thirds times 64, and you can figure that out if you want. That's 4 times 64, I guess 256 over 3 is the final answer for that. Okay, that's all details. Here's another example. Number 2. Find the average value of want to find the average value of f of x equals xy on the region bounded by y equals x squared and y equals x to the fourth in quadrant 1. Okay, it's an interesting question. These power functions, y equals x squared looks like this. Y equals x to the fourth is a little bit flatter, and they intersect at the point 1, 1. And that's y equals x squared on top. On the bottom, that's y equals x to the fourth. And they intersect at 0, 0, and 1, 1. 1 to the fourth is 1, 1 squared is 1. So this is the region, that crescent-shaped region right here. Here's y, here's x. I can't draw a Cartesian coordinate system without putting an x and y on the axes. Memories of my 9th grade algebra teacher, Mr. Miller, come back to haunt me if I don't do that. So I think he's going to come into the room and take a point off. So we want the average value. Average value is we need to integrate the function over the region, then divide by the area. Let's figure out the area first. Area in this case is going to be double integral dy dx. X is going to go from 0 to 1, outside limits first, and the y limits go from bottom to top, so it's going to be x to the fourth over x squared. Okay, I'll let you evaluate that integral. You get y from here to here, plug it in, integrate x, etc. We need to figure, let's just call this a. And then we're going to figure out another integral where we actually integrate the function xy dy dx. And it's the same limits of integration. We're just putting this function in here to add up. Function times area, function times area. It's going to go 0 to 1. And that's from x to the fourth to x squared. Okay, let's just call that b. Then the average value, f average, is just going to be b over a. I'll let you evaluate the integrals. Xy dy is xy squared over 2. Plug in, plug in. You get a big old function of x, integrate that dx, plug in the numbers, and get the answer. So if you have any trouble with that, come to a Zoom session. We'll straighten you out. One more example for this video, and we'll have another video on this topic, actually. So, 3 examples for the first video. Let's suppose we have a region bounded by y equals 5x, y equals 0, and x equals 5. First of all, let's write out and make a picture of this region. Y equals 5x, that's just a steep line like this. And y equals 0, that's the x-axis. And then x equals 5 is a vertical line like this. That's x equals 5, and that's y equals 5x. Of course, it intersects at the point x is 5. We know that based on the vertical line. Plug in 5 times 5 is 25. That's good to know. So this right here is y equals 25. Let's set up 2 integrals. to figure out the area. We'll do a dy dx integral, and then second we'll do a dx dy integral. So you can get used to this way of thinking over here. Well, first of all, outside limits first. X has got to go from 0 to 5. And then the way of thinking for y is lower to upper. Okay, the lower curve is right here, y equals 0. So we go from 0 to y equals 5x. That integral should do it. You can go ahead and evaluate that. Well, this is the area of a triangle. The base is 5, the height is 25. 1/2 base times height. Evaluated, I'll tell you what the answer is, it's 62.5. Now let's do it the other way. Let's do it as dx dy integral, okay? Set up the y limits first, lower to upper. The lower y value is 0. Upper y value is 25. And then x goes from left to right. If you want, when you're starting out, you can even write left, right in here to orient your thinking properly, okay? And these are x limits. So we have this curve here that's on the left. What's x equal? Y divided by 5. And what's x equal on this curve? Well, guess what? It's a constant 5. It doesn't vary. X doesn't vary with y. You can evaluate this, and it should be 62.5 just the same. I'll evaluate this one just to conclude the video. We integrate dx, we get x from y over 5 to 5 dy. Okay, the integral becomes x. We put these limits in. Now we substitute, subtract. You get integral 0 to 25, 5 minus y over 5 dy. Okay, this gives us 5y minus y squared over 10 from 0 to 25. Okay, that's y squared over 2 times 5, which is 10. And you can plug this in. This 5 times 25 is 125. 25 squared, 625 over 10 is 62.5. Subtract that. As predicted, 62.5. You could do the previous integral. You'll get 62.5 if you do it correctly. So, okay, that's all for this video. We'll be back with a second one.